Yeah. Ah. Yes.
That's what I get excited about.
Yeah, nice. Okay. Yeah. Mm-hmm. Nice. Thank you.
That was my album.
Thanks so much.
I love that.
So I'm not sure if it's
That's really good.
depends. Yeah.
Lands. Okay. Swims over.
I love that.
I guess we can start.
A little talking.
All right, so let's start. It's my absolute pleasure to introduce Professor Chinedu Ekuma from the High University. Chinedu did his PhD at Louisiana State University under the guidance of Mark Jarrell. So working on like many-body computational physics, right? Yeah, he's a big expert in computational and theoretical physics. So he then went on to do a research fellowship as a research fellow to work at US Naval Labs, and then got a George Adams Distinguished Postdoctoral Fellow Award to join US Army Labs to do also computational work. And since 2019, he's an assistant professor at Lehigh University, leading a well-funded group on computational physics. And yeah, so he'll tell us about Unveiling quantum quirks, the computational design of materials. Without further ado, the floor is yours.
Thank you, Matthias, for a very kind introduction. And thank you for spending, I normally say this is the best part of your day, 4, 5, 6 is always the best part of, so you're spending the best part of your day with me. So today I'll be sharing with you some of the works that we do in my group, how we are trying to leverage data-driven solutions to help us discover some new generation of material that we hope could help us go a step beyond where we are currently are in terms of energy efficiency, sustainability, and the rest of them. Kind of a guide to what I tend to follow, but if I don't follow this, don't hold me. Pretend you never saw this. As I said, we are pretty much small group, but large comparable to the size of the university and the department. So we are a group of 4 with 1 postdoc. We are trying to hire one anytime now, focusing on new materials design. So if any of you are graduating tomorrow, come and help us design some new materials. I do have some key collaborators. These are all experimentalists. Sina leads the experimental work at US Army, focusing on complex material design. So whenever we discover new interesting material, we throw it to him to see if we can make it. And he has been kind to make some of all those. Recently, we started collaborating with Lupa and Christy. Christy is in UC Davis and Lupa is in Worcester Polytechnic. Again, these are 2 experimentalists focusing on whatever they call it in experiment, but these are high-level all-optical measurements that are only applicable when you're doing measurements for 2D structures. And Srivanus is one of my colleagues at Lehigh. Recently, we started collaborating on doing exploitation, which is a multi-fidelity machine learning approach that could help us do more high-level predictability. Our work, this work, however, are funded by NSF, DOE, and also National Institute of Health. But you will say, what am I doing with the NIH? We do actually have a funded program focusing on DNA sequencing, but I won't be talking about that. So, kind of, where is Lehigh University? I know, just like you, I didn't know about Lehigh until when I started looking for jobs. So Lehigh is sitting right here at the edge of Pennsylvania, somewhere in Bethlehem / Allentown. It's a community of roughly 80,000, but Allentown, which is a bigger city that close to Lehigh, it's like 100 and something. So 150 something thousand. So it's like 200 and something thousand people basically. Small compared to other Pennsylvania areas, but still large enough to maintain a vibrancy. It's a nice place to stay, hilly stuff. So if you want to always keep fit, it's a good place to move around. Moving from one building to another can actually, even if it's cold, you're going to feel some heat when you finish going. The university looks like this. This is a nice place that we normally walk all day. I always take a walk here. It's pretty much, if you pass here, you get my office at the Lewis lab. Computationally, we are sitting here. My office is at this place. This is the Sherman Fairchild, and this is the main Lewis lab. Recently, this is here. So, but recently, okay, what happened? Recently, we've been fortunate. They call it a Health Science and Technology building, but we've been fortunate to also have an office space here, and where students also sit. I don't know which side, but I think, yeah, around here, the second floor. So that's pretty much what Lehigh looks like. But to kind of tell you what motivates the type of research that we try to do is something like this. I don't know how many of you have made it to Eastern Europe. Unfortunately, US has refused to go beyond our buses. This is what we call maglev train, or bullet train as some folks call it. It moves with a speed far larger than that of aircraft. So meaning, had we had a bullet train, my 5-hour plus drive to this place could have taken me maximum of 32 minutes. That is how long it could have taken me to get here. This in China and the rest also use this. You ask, why is it so efficient? It's zero emission to the environment, highly sustainable. It uses a concept of magnetic levitation, which makes the rail and the actual train not to really talk to each other. Superconductivity comes to mind when you say something like that. So these are some of the emerging potential applications where new materials that are driven by asking a different type of question that could lead us to. So this is generally what tries to motivate the type of research that I'm interested in. Sustainability, eco-friendly, solving or answering the big questions like 5%, roughly now 10% of the world energy is consumed just by data processing. Imagine when we ought go into Internet of a Thing and the rest, by 2030, by projection, data processing alone we literally take most of the energy that we need. So we literally need some more energy efficient material. But before I go deeper into what I want to share with you today, I realize there might be some maybe undergraduate or folks who don't do condensed matter in general that might want to know what is then computational physics, right? In the early 80s, before 90% of us here were born, we only know about theory and experiment, right? As things become better, will I say things start becoming worse? I don't know whether things are better now than before, but I'll put it that way. Research-wise, as technology keeps improving, come the idea of computing, where we can no more do pencil and paper work anymore for most of the systems we care about. We now have to solve it on high performance computing. So comes the idea of computing, focusing on simulating models, testing hypotheses. Theory develops models. But I can tell you, you cannot be a good computational without being a good theoretician unless you need somebody to depend on to give you the model to try to simulate. So basically, I was saying distinguishable, but you can be a good theoretician, but you have no clue what computation does. So that is one way to think about it. I always say these three need each other to survive. There are many experiments lying somewhere in the lab that experimentalists don't know how to explain it because there are no theories to explain them. So we pretty much need each other to survive. Experiment need theory, theory need experiment to be able to explain some of the things we are seeing in the lab. So to put it into perspective, the first paradigm is what I call the empirical science, the Newtonian era and the rest, where they were using stones to light their stove and things like that. Then come the second revolution, the paradigm where physical laws, mechanics, thermodynamics, kind of early 90s, then the birth of quantum mechanics in 1905 and the rest of them. That is what heralded the second paradigm. The third paradigm is when computational science, simulations in terms of density functional theory, molecular dynamics, dynamical mean field theory, and other density functional perturbation theory and other high-level theories comes into play. We are now in the data-driven world, where every question that you want to address is no more, this is it. You really need to look at trends. You really need to use data-driven solutions, statistical learning, AI, data mining, pattern and anomaly detection is what is driving the world. I always say data and informatics is like the glue that is holding science. I think the future of science revolves around this glue being able to transcend beyond the excitement that we currently enjoy to actual real applications. All right. Kind of similar to what I just laid down, how then do we do this computation when we talk about computational guided material synthesis? If you look carefully, you see AI technology is like the organizing factor where you have neuromorphic computing, you have cognitive cybersecurity, robotics. These are all potential, not potential, these are all areas where AI have been applied. When I'm sharing this slide is I've gotten asked this question, okay, AI this in physics and the rest, where else can I apply it aside from trying to make new materials? I'm telling you, I remember I talked about anomaly detection here, right? Pattern recognition. You talk about, for example, credit card fraud. Anomaly detection is what it is. Clustering analysis is what we do. And we also use clustering analysis to look for anomaly in material. It's exactly the same idea, different data set to lead to the same conclusion. Neuromorphic computing, I will share with you some of the material stuff that we have that we think could be explored for those type of applications. So the landscape is unlimited of potential application of some of the sciences that are being driven by AI in general. It's not just in material. Those who do astronomy and the rest, you see yourself every now and then applying it to analyze the data. The key question once you have data that you care about structure, property, relation, or pattern, then this is always your go-to. All right, so what then kind of, what I call rationale, you think about what I call a Edisonian era. A Edisonian era is the era whereby if I want to make a new material or computation, I say, oh, I want to make carbon and hydrogen. I take carbon and hydrogen and I simulate them. That era has gone. I will ask you, what of the stoichiometry? What if I do carbon 3, hydrogen 2, carbon 2, hydrogen 6? Those are potential that I can also build, and each of them might actually lead to different physics. Now, you can't do that. You can't effectively do all of them efficiently at the same time, because if I start generating my potential combination, the compositional space could be exponential that I won't be able to do it. So what we are trying to do here is we want to accelerate discovery. We want to make the time it takes for new materials to be found faster beyond a Edisonian system by using data-driven solutions. Informed decision, remember, you can actually do inverse material design whereby I can say I want a particular property and I would make my system kind of converge to that type of property. Optimize resources. Think about trial and error. If you have to make all of them, you're going to build experimentally. You have to make many samples. That is wasting of resources and also time consuming. I think also there is this diffusion of, science, from computer science to physics to chemistry to all other engineering, whereby your theory alone is no more enough to carry you through some of your day-to-day routines that you either need to have a computational science body to put you through some of the things you do, or you learn it by yourself. So there is this convergence of science. And again, addressing sustainability, as I alluded to earlier on, I think new materials could in general contribute to eco-friendly materials, thereby making scientific relevance of materials more acceptable in general. So these are kind of rationale or why we try to do this type of thing. All right, with that being said, how then do we do data-driven design of materials? Now, generically, we start by building blocks. You have large configurational space. These are potential candidates. You assemble them into all these potential candidates. You set some parameter, you screen these guys to get some small hint. So this screening could be, okay, I want these systems, those that are energetically stable. How? Well, you can calculate the total energy of the system and calculate their formation energy on the fly. And you see those that with positive formation energy, I want to throw them away. That will reduce this guy to this small chunk. Then you now ask this question, okay, now these ones that are stable energetically, I might also want to do dynamical by looking at their phonon, or do mechanical by looking at their elastic constants. That will also reduce it to smaller target materials that you can either do more high-level calculations like GW, DMFT, or any other type of high-level theory to confirm whether the physics you have at the back of your mind is achieved or not. If it's not achieved, you go back again and iterate over until you get reasonable convergence that you can say this is enough for you to start piecing it. Think about this is a real computational synthesis where you start with molecular fragments, some molecular structures, 10 to the power 6 of them. At the beginning, you do your initial screening, you reduce it to 10 to the power 6. This is where you do your machine learning prediction. Then you apply some quantum chemistry simulation in terms of density functional theory, reduce it just a little bit. Then this is where your expert knowledge comes in. I need certain material that meets certain threshold, takes it to 10 to the power 3. Then you try to make them and test them. You can do all of them computationally on the fly. You try to make them and test them, then you end up with just 10 to the power 1. So this 10 to the power 1 scenario is whereby you now do more high-level calculations to better check the problem you had in mind. So in the realm of machine learning, how do we do that? Well, for some of us that are not too conversant with machine learning, we have two types of what I call traditional machine learning. We have the supervised and unsupervised. The supervised machine learning is used to train labeled data. Labeled data in sense continuous data set like your energy bandgap. We also have what we call unlabeled data. Unlabeled data could be a question like, is this material metal or semiconductor? A true or false like problem is what we normally refer to as unlabeled data. So generally, you start with either this or this. You do what we call feature engineering. Feature engineering, again, is achieved based on your domain knowledge, right? Like, suppose I want to design a material for, say, optoelectronic application. Well, at the back of your mind, you said, I will need the energy band gap, which will be your target in machine learning language. Then your lattice constant could be a factor. Your electronegativity could be a factor. Your composition could be a factor. Stability in terms of, say, your elastic coefficients or their Young modulus could be a factor. All those that I've named is what we call features. Or that is where the ability to select certain features that meet those is what we call feature engineering. When you do your feature, after your feature engineering, you do what we call data splitting, meaning you split your data set randomly into training and test. Some people go beyond that. You have training, test, validation. But generically, if you're too in a hurry, you can do training and test. So you keep at least 20% of your data set for testing, then you take 80% of your data set and train your model. So you see what I will hold out. This is what I call validation. These are like your holdout that you use in validating. Then you train, it converges, you evaluate again, get your model. You take your model now, you can decide to make prediction. Caveat. For every machine learning model, you only get what you put in. Meaning, you cannot train this guy to predict orange and you want to check whether he can tell you whether this is an apple. It will always tell you it's not an apple because it doesn't have information of what apple looks like. So a typical example in material workflow is think about when you train your material to only predict structure with hexagonal structure. You cannot be forcing it to predict a structure with monoclinic structure because it was never exposed to that type of data setting to start with. So, that is one thing that I think people is not generally aware of, that you get what you put in. Anyway, let's move a little faster because I'm looking at my time. I've literally gone by 20 minutes and I haven't even started. So, material-wise, what type of material are we generally interested in? For me, I'm interested in these 2D structures. I'm also interested in perovskites. One thing about this type of material is that correlation is everywhere. In 2D structures, they are due to quantum confinement. In perovskites, they are just due to their complex structure. That mainly this guy can be oxygen, it can also be chalcogen like sulfur, selenium, and the rest of them. And diverse applications, you can see catalysis, spintronics. I won't go into what each of them is, but those are potential applications of this type of materials. Again, in the periodic table, you can see them like this. And why are they also interesting? You can see from graphene to hexagonal boron nitride. This is what I call their poster child. Even though it's not good for anything, as it is alone, you always have to do something to it. But this is what motivates everything after here. So you're starting from zero band gap system to a gap system of as large as 6 electron volt. So by extension, you are covering the whole electromagnetic spectrum. So there are many, many potentials to design many, many things from there. I don't know what is cutting off here, but it seems as if I cut off something. For us, we've been kind of asking a different type of question beyond just 2D structures. Because I believe that 2D structures at their extreme limit is not useful for anything because it's just too hard to make devices out of them to preserve their unique properties. We have to do something different. So we've been exploring organic, inorganic, electronic intercalation, where you take these 2D structures, you sandwich them, right? You sandwich them with molecules. Now, why are they interesting? Organometallic molecules, for example, or conjugated molecules have been studied for decades for photovoltaic applications. So we want to bring the best of the two worlds and merge them together and pray hard that those properties mix and match each other to give us something better. As you can see here, if you look at the absorption spectra, the ones with this MOS2 and the molecular combination is the one that gave us the best response within this energy window. Remember, this is the energy window where visible light is included. And as you can see here, their mobility is far away here. We also need systems with relatively sustainable mobility so that we'll be able to make them at room temperature. And the good thing about these guys, they have this large area surface. 2D structures is naturally good for that. So they can absorb those sunlight, and they are structurally tunable because you can mix and match these guys. Another good thing is when you make these new structures, computationally, could experiment be able to make them. As it turns out, it's actually easier to make the intercalated structure than to grow 2D structures. So it's a win-win for anybody who wants to look at that. So there are many robust traditional way of growing crystals that could be applied to grow these structures. In terms of the efficiency in field effect transistors, which is what we end up having to make them, they have these nice responses, and this is their PCS. This is graphene heterostructure with some 2D perovskites. As you can see, these guys have what I just showed here is in their application as a neuromorphic system. I don't want to touch there yet until I get to the when I've introduced them. So this synapse is like representation of neurons in terms of the equivalent of neurons when it comes to the way the brain is configured. So traditionally, when we talk about interconnection, we take 2D structures. There is something unique about them too. This gap here, this gap between them, they are intrinsic, meaning you really don't have to do anything for the gap to be there. It's of order of 3.5 to 3.7 Armstrong. So you can throw in lithium, potassium, or anything there, right? That is a traditional way to make them. And there are many ways. You can do electrochemical, you can do chemical, you can do a bunch of other ways which I don't know, but there are many other ways, chemical interconnection, electrochemical interconnection, and the rest that you can go there. The question we want to address is, instead of putting elements here, we want to put molecules, something like this. We want to put molecules in between here, something like this. And as you can see, this is a sample test. Again, I have color mismatch here. There is something here. This is the energy band gap for MOS2. There are many molecules down here representing each of these lines. I got to fix that. There's another thing unique about this type of material design. This intercalation process is reversible. Unlike doping or other processes that we are generally used to in the lab, where once you form it, you can't break them apart, this process is reversible, which is why it's been explored for neuromorphic system, because you need to be able to intercalate and de-intercalate without destroying the host system. All right. Again, these are a bunch of other systems that I'm just showing you how we take this type of molecule. This is what we call the metallocins. We put them in between hafnium disulfide. We can look at their transport, their charge density distribution, and a bunch of other things to know the character of the molecules in between. So this is the state of the art. As I said, what we are doing differently is coming to this realm. We, instead of using elements, we are using molecules. So, but how do we do it, right? There are many ways you can mix and match the molecules. This is where what I tried to introduce earlier, and I'm trying to go a little deeper on how we try to use machine learning to help us accelerate this process. So we have a bunch of building blocks, 2D transition metal chalcogenide. A transitional metal chalcogenide is any transition metal like iron, cobalt, copper, chromium that has forms a compound with chalcogens as sulfur, selenium, and tellurium. So that's transitional metal chalcogenide. You have to remember, you can also have transitional metal monochalcogenide when you have something like GESC. But when you have dichalcogenide, it's like MOS2. So there's two there chemistry-wise. So we are looking at both the TMDs and the TMCs. So that's what I call TMCs. Here is transition metal chalcogenide. It can be di, it can be mono. So that's like our building block. Here, we can, how do we get our molecule? PubChem, for some of us who do some biological sampling, PubChem has over 14 million experimentally synthesized molecules. So we can query the PubChem repository by using their API. And you can put a bunch of constraints because there are just so many of them. We can put what we call plenarity, and we can limit the number of molecules we want. Here we limit it to 30, and then we can grab as many as we want to build our structure. Then we do property calculation, band gap, elastic constant. This part is used to check their mechanical stability and throw away those that are not stable on the fly. Then we do have some experimental feedback. I won't go deeper into this part here. This is the multi-fidelity modeling, which is like a reinforcement learning process whereby we take, I'm going to explain that shortly, we train low-level data to be as high accuracy but small data set. So there is an inherent inner loop of multi-fidelity modeling that we use to improve the predictability of the overall machine learning processes. There's also experimental synthesis of it. Specific to the example I want to share with you, again, this is our building blocks. Here I want to focus on what I call planar structures. Planar molecules are those molecules that don't have rings. They are just plain, like plain on this way, similar to this. So again, this is our building block. We have PubChem building blocks here, form bunch of conjugated system, plausible 2D materials, check their stability, view this library, do some high-level theory calculations on them, and look for some of them. But technically, what we did is to design a computational framework. Here we've chosen, there are 24 transition metal chalcogenides when you form them as bilayer, 24 of them. Now, from the organic molecule side, we obtain 14,000 planar structures. So you have to do around 336,000 independent DFT calculations. Not that it's not possible, but do you actually want to do that, right? So what we did is we created a framework that uses Bayesian optimization. I will share with you how, kind of a quick overview of how that is done based on what we call bootstrapping. That could actually limit to the number of calculations that you do here to like 2%.
Does the density of intercalates vary also? So when you intercalate, I haven't ever done that yet. Is there a stable density of things that go in there, or is that can that be varied also? Is that another parameter in this space?
So basically, we don't have to worry about the density because the way we are doing it, we have a bilayer. We're intercalating one molecule at a time.
Okay.
You see, we are not because that is the simplistic model we can build when you're doing a high screening system. Yeah, so we don't have to worry about the density at this point.
Okay.
But that's a very nice observation. All right, so as I pointed out earlier on, so we have to do 336 calculations. Instead of doing that, we start with a randomly selected 500, meaning you randomly select your whole 336 configuration, you randomly select 500, and we calculate what we call the intercalation energy. The intercalation energy is the energy cost of inserting a molecule in between that van der Waals gap. So we calculate that, then we build a bootstrap model. A bootstrap model is an active learning Bayesian optimization. Generally, this is how it looks like. Again, I'm not going to go into this. You build a bunch of surrogate models, then you run them over time and check their convergence, just to add. So the key factor about this guy is resampling. I'm trying to summarize this as much as I can because it's more complicated than it's not as simple, but we have limited time. But so if you want to talk more about it, I can go into detail later on. It's a resampling technique. But the powerful part of the bootstrapping, being that it's a Bayesian optimization approach, is that it doesn't make an prior assumption about the distribution of the system. So it ends up just predicting it by its own. So with that, we can do bunch of it. For our case, after 5 iterations, we pretty much converge to our top 50 materials that we care about. So that's kind of a quick summary. I know it doesn't give you the whole picture of what Bayesian or bootstrapping approach generally is, but it's a well-established statistical approach that is applied when you don't know the distribution of the data set that you care about. But here we are tailoring it to use it as an active learning back-end envelope in our machine learning architecture. So I talked about, remember, I told you that we have this inner loop where we do multi-fidelity modeling. So that inner loop involves, you have a low fidelity data, many of them. Now, you have high fidelity data, but very small. But you want this high fidelity data, could be experiment or GW, because you need, suppose you want to predict band gap. Density functional band gap, for example, is 40 to 30% inaccurate. But if you're actually going to make a prediction, you want a data set that could actually make prediction. So this is what the multi-fidelity does. It does a transfer learning between these two guys to make this low fidelity data to be of the same accuracy as this guy. Again, a very simplistic explanation of a very complicated process, but that is what does happen. It's an active transfer learning approach that you can use to make a low-level data to be as accurate as a small data set of high-level data set. Why is this approach different from what I told you earlier on, supervised and unsupervised machine learning? In traditional machine learning, isolated single task, generally the knowledge you get is not retained and is not transferable. You learn, you throw it away. In transfer learning, the multi-fidelity approach, for the learning of a new task generally relies on the previous task that you've already known. So learning process can be faster. Think about a child learning to walk. The more he keeps doing it, each day he or she improves on the ability to move further. That's exactly what happened. While this guy is like a child who has refused to walk. He wakes up every day, doesn't want to try again because he's afraid of getting injured and stuff like that. So that's the way to think about what this guy does. Here, knowledge is constantly being built until you make yourself better every day. That's the difference. Specific to our case and how we're able to use it to make more better informed decisions, what I'm sharing with you here is the energy band gap of some material. Again, I selected 3. Here, more or less, they are poster child, some large band gap system, and small band gap system. So this gap is about 6 point something. This gap is about technically 3 point something. So this green one is what density functional theory predicts, which is what I read as low-level data. This red one is what experiment measures. Then after our multi-fidelity training, this blue one is what we obtain. Remember, if you take the error in this guy, this is more than 50, this is more than 30, this is at least 15. As you can see, with our multi-fidelity modeling, these positions are within the error bar of this experiment. So we can actually make these data sets that are of low-level quality to be of very high-level quality, thereby enabling us to make more informed predictions. Again, this is kind of what we call multi-targeting approach, whereby you can systematically both predict their mechanical stability characterized by their Young modulus and the band gap using deep neural network. So this is kind of just a snapshot of how we can achieve that in some of these processes. Even though it's not directly tied to this, but this is also one way to screen materials faster, where if you're interested in optoelectronic materials that are stable, you can both do that on the fly using deep neural network to do multi-targeting predictions. All right. I've gone through I hope I'm able to tell you how it works. There are many moving parts. I try to put them together as much as I can. But you ask, okay, what are their potential applications? So I will quickly go to some of their potential applications. I talked about this neuromorphic computing, which is nothing but something that could work like the human brain. Some basic definition is like, can brain-like computing device based on new material concept and system be developed to dramatically outperform conventional CMOS? This is conventional semiconductor metal oxide systems. Why? Because we basically have computer in our everyday, Just like me, and I know many people, you wake up at the middle of the night to check your phone to see whether you have new messages. You're burning data. You're sending this data you were throwing left and right needs to be processed and stored somewhere. So with that, we really need to figure out how to make battery life longer and stuff like that. Again, we believe that these neuromorphic systems, because they lack non-volatility, meaning they behave like an analog computer or analog system, like our new architecture is like zeros and ones. The human brain behaves like an analog computer because everything is continuous. That's similar to what we are trying to achieve here, basically. So 2D materials, because they are flexible, because they are tiny, we believe, because the channel length needs to match the scaling, which is one problem with current CMOS, we believe it could be used as an. I'm going to skip some of all this. These are some of the basic information of what it entails. Again, this is our current information and storage and processing are disentangled. The human brain processes where it stores the information is also where it processes it. So like in your computer, you have the hard disk and the processor. We don't want that. That's why it heats up all the time. We want to be on the same chip. And that is where the human brain is one of the most powerful supercomputers ever known to man. So I'm going to also skip that. But how do we make this type of materials in general? This is kind of that stacking I told you. Remember I told you I chose this intercalation because the ability to intercalate and de-intercalate gives us what we call dynamical reconfiguration that could be harnessed for neuromorphic application. And these layered structures comes in handy for that because their natural van der Waals gap enables anything that you put in there to not actually bond with them ionically or covalently. They only talk to each other through van der Waals interaction. Because of that, they are easily removable and also replaceable, making this type of systems a go-to place to be able to engineer this type of devices. For us, this is an example of how we start some of all this. Again, sorry for this font mix-up. But this is that of hafnium disulfide with COCP2 is cobalt. This is what we call cobaltocene, and CrCP2 is another molecule we call chromosine. I showed you the structure before. This is a first back-end envelope calculation looking at the electronic structure and their work function. Remember, you can use the work function to know whether you have an N-type or P-type and stuff like that, just to give us a general overview. And we did some experiments by our collaborators at US Army, and they're able to quantify based on their electronic, that is photo emission spectroscopy, the type of character that we are seeing. They actually also tried to look at the Raman and a couple of other things. And we saw there is this charge transfer between the molecule to the host system, which is also quantified in the way the band edges move when they imaged it. They also, this is what I was referring to. You can see, you can form this hysteresis like approach where you can both reintercalate and deintercalate the system without destroying it. That's the beauty of this process. So because of that, but something very dramatic happens when we put this molecule. This is what we call the cross-plane and in-plane transport. The cross-plane transport increased by almost 400-fold, meaning 7 to 400 to roughly 400 and something, basically. Because of that, it's a general way to tell us that we can easily dynamically change this system by changing anything within the local environment. Actually, I think we are the first to actually demonstrate intercalating molecules in 2D structures. And this was covered in various news media where this thing was done. I think I'm running out of time, but another material we discovered is this, we call them perovskite-derived all inorganic, perovskite-derived all inorganic 2D structures, where we remove the 2D-like structure from inorganic perovskites because it has lead and is unstable. With the advent of 2D structures, we take it and make it 2D and look at the electrophotonic response. For this particular class of material, we've been discovering something that is unusual. They have this flat band near the Fermi surface, and they have a lot of spin-orbit coupling dependencies. Quite flexible, meaning it can be used for other biocompatible applications and stuff like that. But they also have this huge electronic response within the near-infrared and visible regime, which is where sunlight operates wavelength like. But we also looked at tuning it with strain. You can engineer a bunch of other properties in this guy. Pretty much, we have an in-house code that we can use to look at mechanical stability. We just got angry and decided to do it for all other isoelectronic parts of all this. So if you're ever interested in this, we have all the CIF file in our GitHub where you can get some of them are not stable though, but we indicated those that are not stable and look at the overall stuff. Then we started doing isoelectronic substitution by removing some of the iodine and putting in chlorine, and we are seeing something very, very unusual. This binding energy that we are seeing here is exciton binding energy of almost 3, which is the highest I think I've seen in any material in general. Now, another thing we've been looking at, I'm going to round up this one very fast, is potential application of some of all these materials. There is this theory, it was theorized by Louis and Martini in 1997 of intermediate band system, which is, think about you have a material that is insulating or semiconducting, but you now have a mid-gap state living in between them. These mid-gap states experimentally could only be achieved in a heavily doped semiconductor. Well, heavily doped semiconductor suffers from non-radiative recombination, which will destroy any potential application. So we got one of the systems that we worked on, we saw this emergence of this intermediate band states only if you turn on many-body interaction, meaning it's driven by many-body physics. And being that it is intercalated, we also believe it meets the Anderson regime of being slightly disordered, but not heavily doped. But the most important thing here is that this intermediate band states is driven by many-body interaction. So what we did is, well, we took, this is their optical absorption. This spectra is at the level of GW, solved by solving two-particle problem, GW plus beta safety equation. That is the only way you can extract exciton physics. This is excitonic physics, not carrier-like electron. This is their loss function, showing all these huge peak structures within, again, the energy wavelength that we care about. But that's not it. Then when we made this, we got some of our experimental colors. This paper have been published, just came out yesterday. But they made these samples and they were able to see some of the physics, which is the response, and they made some toy model of what they think is going on. Remember, copper is a zero valent element, meaning it doesn't really give much per se. So we are excited about it. We are looking at other potential applications like ultra fast dynamics and stuff like that, apart from photo. But here I'm focusing on the photovoltaic for now. We take this our new materials and build a solar cell. So these are we calculate the external quantum efficiency of this solar cell. This is done using a transfer matrix method. Transfer matrix method is a numerical exact approach. So the input in doing this is the complex refractive index, which is the real refractive index and extinction coefficient, which you can easily derive from the complex dielectric function, right? So that is what serves it here. But the most important thing is this is a huge external quantum efficiency is at least at this wavelength of interest is independent of thickness. Because referee was asking us, oh, because you're destroying the 2D structure, you're making this thing thicker. We say, well, yeah, we wanted to show that you can actually scale this by making it a little thicker. It's still a nanofilm, but the physics is independent of thickness at this small regime where we care about. So we demonstrated what I will say is we achieved what Mathieu and Louis theorized in 1997 by designing a strongly correlated system that met the Anderson-Mott limit for designing an intermediate system for photovoltaic application. So we are still battling with referees to have these guys published, but that is what we've seen so far. Again, I think I took a little bit time, 4 minutes, but that's the end of my talk. I think data-driven approach could be the next thing in literally everything that we do. For us, it has helped us tremendously in accelerating the process of building new structures and new materials that we couldn't have been able to do. As I shared with you, we observed some interesting physics in hafnium disulfide intercalated with this type of molecules that could be exploited for neuromorphic application. In this all-inorganic derived perovskite, we saw some response that are appealing for PVC and valentronics. And in GEX, we observed many body-induced intermediate band states, again, that could be exploited for PVC, but we're also looking at it for ultra-fast dynamics application, because these guys, because of the way they have this type 2 staggering and they have this generic flat bands, it could be a process to look for Bose-Einstein condensate, like exciton condensate. So experiments, they have been hitting their head and trying to see, be able to see. For us, we can actually do calculation and check, but most of the times, calculations don't tell the full story. You always need the experiment to back that up. With that, I will say thank you so much, and sorry for taking 5 minutes or so beyond what is needed.
Thank you. Are there any questions for speaker?
I have a question.
Yeah, sure.
What determines the materials that you choose from when you're making your first big group? Like specifically for the neuromorphic computing, are you using chemicals that can be found in the brain or any inorganic material?
Well, that's a good question. No, we generally look for something out of the ordinary. Think, for example, like that of hafnium-based system. We know hafnium is a boring insulator, right? But here, we are seeing when we intercalated that, we have some magnetic properties emerge just by putting those molecules. Then we do have some dynamical tunability of the energy band gap and stuff like that. Remember, some of the calculations you're talking about roughly in the order of 500 100,000 to 300,000 different samples. So you can put a constraint that spits out, say, top 5 that you can do some major, more refined calculation on. So generally, when we get our topmost, we still need to do some high-level calculations because we really don't even know fully. Biologically, they know what the human brain contains, but it is not really mapped one-to-one material-wise. So the way we think about material that could be used for brain-like application is 1, non-volatile. 2, it must be highly dynamically reconfigurable, meaning you should be able to change the property on the fly without changing much of the local structure of the system. So those are the few things that we look for. Think about when I told you we're able to tune the implant transport by 400-fold. Those type of huge change is like signatures of potential material that could be applied in this space.
All right. Any other questions? Yes.
So when you're making the first cut, like for stability, are there any assumptions that you anticipate might not be true? I'm thinking particularly about how 2D materials weren't supposed to be stable enough to be realized. So do you think maybe things are being left out that we might pick up again?
Yeah, that's a very important question. Was it yesterday there was a proposal I was writing that I was answering that question? Normally when we do material screening, we only look at the energetics, meaning we check whether the formation energy is negative. But we are not just doing that. We are checking the bond criteria. Bond criteria is encoded in elastic constants. So suppose we know the bond criteria for 2D structure. 2D structure is hexagonal. Your C11 must be greater than C12. Even though both could be positive, but if C12 is greater than C11 or C22, the material is unstable. That is one. We can check that on the fly. Secondly, we can calculate the eigenvalues of all the components. All the whole eigenvalues must be positive definite. So my belief is with those checks, it is very, very unlikely that we are going to miss or characterize a supposed unstable structure to be stable. But based on energetic alone, I think you might be able to make that mistake.
Other questions? Yeah.
Aren't the question you're asking a little bit like asking a question like how does a human brain function? Because you've got all these bits and pieces which do certain things. You're trying to put them together to make some machine which does certain operations you want. Am I right?
Almost. So the human brain, we know how it works, right?
Sorry?
We know how the human brain works. It works like an analog computer, meaning it doesn't recognize information.
Yes, but I mean, if you think about the basic machines in the brain, they're unbelievably slow compared to what's in the computer.
Not necessarily. The human brain is known to process information faster than any.
But this is the question: how does it do it? Because each individual element in the human brain is much slower than an element in a computer.
But it has 10 to power 11 neurons that connects.
Right.
To do that.
Right.
So individually, yes.
Yes, but somehow the nature has learned to connect these elements up in such a way that to basically end up with an incredibly powerful machine, which does certain things extremely well, other things not so well.
So the way I think about it is, I skipped that slide. The way I try to think about it is this. To kind of put it into context is to look at something like this. So, let me go here. So the way I try to think about it is it's still far away. Remember I showed you this neural network stuff that are connected? And we can see that when we use deep neural network to do data processing, they are far, far faster. The reason why they are faster is because you do not have a single, what we call single worker. You have workers, even though you have a weak worker, they carry each other along so that they rub off each other's strength and make each other better. So that's how the human brain is like. The human brain is very slow on single level. But because there are so many, you cannot pack 10 to power 11 chips on one, sensors on one chip. That is how much you need to be able to get one task that the brain performs. So technically, because of this analog nature, it has this massive parallelism that helps it to speed up data processing and information retrieval, because again, they are also living on the same place. Unlike our supercomputers, the memory and the storage are disentangled. There is this communication lag that you have to also pay for. The brain doesn't pay for it because both information storage and the processing stays in the same place. So because of that, even though it might be small, and also look, the brain only needs approximately 20 watts to process that information. But our supercomputer needs roughly 1 megawatt to process this same type of information. You see the energy dissipated, but this guy, because he's massively connected, is still far, 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 orders of magnitude faster than the most powerful computer we know today. There's no anything that comes close when it comes to information processing. You might think it's slow the way it's doing it, but I'm telling you, it is orders of magnitude faster than IBM supercomputers.
But I mean, your statements are sort of, I mean, doesn't everybody knows these statements to be true? Because it's obvious. Because the brain is phenomenal at pattern recognition, whereas a really powerful computer sucks.
And they suck because they are transcoding this information as yes or no, zeros and one.
Right.
The brain is connecting them as a continuous data, which in the new era we call it, in material we call it synapses. You build synapses to mimic the human brain neuron.
Right.
That is the way we are trying to go beyond zeros and one, so that you create this continuous data, kind of a delta function like, that kind of broadens your zeros and one to be no more integers per se or standalone. So it's a far away from where we want to be, but starting to have this type of conversation and trying to build synapses or brain-like, neurons-like in material world is a good place to start having this type of conversation.
Isn't that going to cause a few problems? Because if you're going to have a continuous rather than on-off switches, you have to be continuous. It's not liable to introduce also errors.
You can turn it off and on. That doesn't, being continuous doesn't mean you can't turn it off and on.
No, I know, but still, doing things not on and off, but more continuously allows more information to be processed. But you have to have the worry about the errors.
The error is pretty small compared to standard CMOS. At least the ones that IBM and the rest have tested. The error is pretty very small, which is what quantum computing is trying to do. Is trying to systematically improve the error in the calculation. Without going beyond traditional CMOS, there couldn't be any improvement on accuracy of quantum computing.
Yeah, I mean, but a computer's terrific at doing sums. It does sums incredibly well, incredibly accurately. But something like a brain Not so good.
Oh, depends on how you look at it. Depends.
Well, look at any human being. I mean, they're not very good at mental arithmetic.
That's what you think, but the brain is the fastest supercomputer known to man. It's not debatable, you know. It's orders of magnitude faster than the fastest supercomputer ever designed. It might look slow, but you forgot the energy and the data fed into these computers before they start giving you those information. What am I saying? I will give you a counter argument. If you feed the brain those information over time, think about a kid who does multiplication. If he or she starts to practice it, you say 2 times to tell it, but before then it doesn't. He's very fast at recognizing pattern and he can say without thinking. It's the same thing with this high-level calculation that you are referring to, because you haven't really exposed the brain that much to look at it over time. If you did, I'm telling you, it's going to solve it before you even say jack. You've seen kids do this high math competition where they say spell long word like 25 distance. They spell it before you say jack because you have been exposed to this over time. If you bring a kid that hasn't been exposed to it, he won't even know where to start, he or she. It's the same similar thing here. If you expose the brain to those data, it's going to be far, far faster than those supercomputers. That's and I think there are many, many things to prove that is possible. And
you're probably right. I mean, what are these examples? These idiot savants who can do who are complete morons in many ways, but can do certain calculations unbelievably quickly.
Exactly, because they have been doing it. They have been exposed to variants of it that they really can't. They don't have to think to answer it because it's already living in their brain that they know it. You know. Just like maybe you're preparing for exam, if it's an objective question, sometimes it's just before you finish reading the question, you know what to take because you've looked at it over time. But he or she who didn't look at it will stay there and stare for it till exam ends, and it won't even know. It can't even narrow it down to 2 possible choices. That's the brain. Expose it to pattern, it's going to do magic.
Okay. Thank you all for staying longer. Thank you, Chinedu.
Yeah, but that's an interesting conversation, though, the way to think about some of these things.
Yeah.
Thank you. All right.
It was good to see you.
Right.
Thank you.
An exciting talk.
Sure.
Yeah, it was great.
Yeah, let's see what we can, push together on some of all these things.
But do you understand correctly? Like when you do these, I mean, from the examples that you gave, like sometimes you screen like these. Okay, you have these methods that make it faster and they allow you to only screen a subset. But out of the subset, you then say, okay, here's my most interesting material, and that's the one that you give to an experimentalist. Is
You
that
do
how it works?
further calculation.
Of course, okay.
Then
Some high level.
Yeah, give it to them.
Got it.
Maybe you can't give them more than one. Basically.
Yeah. Yeah, so that was my question, because I mean, on the other side, like, it's not really something I've thought about, but I mean, experiments, I mean, ideally should also be like automated in that sense, right?
Yeah.
Like, say you come up with 100 structures, have some automated machine like build all these structures and so.
We actually had one time when we wrote them. They did for 20, right?
Oh, okay.
Experiment, so because they were proposing that we get top 50. Then experiment we do feedback.
Wow. Okay.
So we did 20 to demonstrate it.
Wow.
That is possible for that subclass. That's the one I told you we came very close, but
Yeah.
we didn't get it. So.
I mean, sometimes I'm not sure. I'm not a chemist, but sometimes I feel like doing synthesis is not always. It's not like it always works for me.
Yeah.
You just change the element a bit, just suddenly it doesn't work. You have to do some major adjustments.
I don't know how they do, but they were able to do it for a couple of the molecules.
Yeah,
using
great.
one 2D host.
Okay.
They didn't change the 2D host.
That makes sense to me. That makes sense to me. This is the first polynomial. This is right. Yeah. So if we go back to the hotel, you can actually walk. Did you walk up here? Ah.
Just